Okay, I'm back. Sorry. I know that Edmodo will only let you post 15-minute videos, and that was 15 minutes. So here's sample problem number 2. They give you this reaction, and they want to know what is true of the relative rates of disappearance of the reactants and appearance of the products. And choice A says NO appears at twice the rate NOCl disappears. If it would appear at twice the rate, it would have to have twice the coefficient, and it does not. It has the same coefficient. So let's get rid of that choice. That can't be a choice. Choice B says NO appears at the same rate that NOCl disappears. This would indicate that they have the same coefficient, which they do. So I'm thinking this looks good as a choice, but I always want to check my other choices. NO is half the rate. No, they have the same coefficient. Cl2 appears at the same rate as NOCl disappears. No, they have a different coefficient, so they can't be the same. And then letter E, Cl appears at twice the rate. Again, that would mean it needs twice the coefficient. It only has half the coefficient. So it actually appears at half the rate that it disappears. So the right answer here should be B. For the next one, I'm just going to put it on the screen, and I'd like you to try it. It's a little bit more complicated, but I'm sure you can do it this morning. So here is the next problem. Sample problem 3. It's a hypothetical reaction. Okay, we have 2A plus NB goes to make QC plus RD. And I give you their rates. This is the rate of A, the rate of B, the rate of C, the rate of D. And I want you to work backwards this time and use the rates to get the coefficients N, Q, and R. You'll need to pause it here because I'm going to move forward. Okay? Section 12.2 deals with the rate laws and how we can write a rate law for a reaction. Okay? The rate, when we do these reactions, we ignore the reverse reaction for the most part. We perform them under conditions where the reverse reaction does not happen to an appreciable extent. So it's not like we're ignoring them. It's just like that they're not significant. Okay? So the rate is equal to K. Okay? K is a rate constant. Kind of like an equilibrium constant, except the units are important. We will need to know the units. It is not the same as the equilibrium constant. So it's equal to the concentration of your reactants, A, B, and C. A, B, and C. And then A is raised to the X. Now, X is not 2. B is raised to the Y. Y is not 3. And C is raised to the Z. So these values, X, Y, and Z, are what we call orders. Okay, X is the order of A, Y is the order of B, and Z is the order of C. And the orders are not necessarily the coefficients in the equation. That is super important. X, Y, and Z can only be determined experimentally. And A, B, and C are the concentrations. The products are not included in the rate law. Okay, so again, a few important things about the rate law. The order X, Y, and Z and the rate constant cannot be found simply by looking at the equation. You must determine them experimentally. We use a method called the method of initial rates, and it's, again, very important that you note the order is not the coefficient. Okay? There's two main forms of rate laws. Oops, sorry. Okay, we already talked about that. There's two main forms of rate laws, the differential rate law, and that rate law expresses the relationship between rate and concentration. If they just ask for rate law, they want this one. They want the differential one. Okay? The other rate law is the integrated rate law, and that expresses how concentration depends on time. And we'll deal with that one next. Okay, the method that we use to determine the rate law is called the method of initial rates. And you do a bunch of different experiments under differing concentrations. Okay? We always have this generic form of the rate law. So if I look at the equation, I can write a very generic form of this rate law. It would be rate equals K times concentration NH. Can I just copy this? Let's see. There we go. Do that, it's easier. NH4 plus raised to some power, so I'll call it the N times concentration, oops, sorry, still there, concentration NO2 minus raised to its power, whoops, which will say, I don't know what that would be, M. Doesn't really matter. You can call those orders anything you want. Okay? So that's the generic form of the rate law. Our job is to figure out what N and M are and what K is. So we need this, and we need this. And we're going to use this data up here to do it. Okay? So that's what we'll use to do it. Now, how do we do that? Okay. We can determine the values of N and M by looking at reactions where the concentration of one of our things is constant and the other one changes. Okay? So if you notice in comparing experiment 1 and experiment 2, the initial concentration remains the same of NH4. Okay? The concentration of NO2 doubles. So this goes up by 2. And when that doubles, this also doubles. So if one's constant, the concentration of one doubles and the other doubles, okay, that tells us something about the order of NO2 minus, and we can actually calculate what we have. If we write rate laws for these, we would have for experiment 1, it's very hard to write with this. Rate equals K for, and we have the rate actually, don't we? So let's plug that in. Let me write this and pause it, and then when you come back it'll be typed. Okay. What I've done is I just plugged in data. So I took our rate law, and for experiment 1, I wrote the rate, which is 1.35. I wrote the concentration of NH4 and the concentration of NO2. I did the same thing for experiment 2. And then I compared. I did a ratio of 2 to 1. The reason I did experiment 2 over experiment 1 is because the rate's bigger. Okay, so now you're just going to do the math on these. The K is constant, so you're going to cross that out. And this is constant, so you're going to cross that out. So you're going to divide these. And if you divide the rates, 2.7 times 10 to the negative 7th divided by 1.35 times 10 to the negative 7th, you get 2. And now I'm going to divide these, the concentrations, 0.01 divided by 0.005, and you get 2. So now the question becomes, what can you raise 2 to give you 2? And that would be 1. So we know the value of M is 1. And we can say that the rate law is first order with respect to NO2 minus. We can do the same thing. If we do the same thing for experiments 2 and 3, you will get N equal to 1. So if you take, 5.4, I'll write it down for you. Just let me pause. Okay, so I did 3 over 2, and the reason you do a second analysis is so that you can get the order of N. You want you want the NO2 concentration to be constant this time. So now this guy cancels out, and this guy cancels out. So you do the math here, you divide those, and again, you get 2. And you do the math here and divide those, and you get 2 to the N. So we're in the same situation. What can you raise 2 to give you 2? And you get 1. So we are also first order with respect to NH4. Okay? Which means our our rate law can be now, we can substitute back in our rate law over here where we wrote the general form of the rate law. We now know that this is going to be a 1 and this is going to be a 1. Okay? So rate is equal to, this is what we now know. We've used this data to find our orders. Now we can also use this data to find our rate constant, and we can find something called the overall order for the reaction. And all that is the sum of the orders. So the overall order for this reaction is 2. Okay? And now you can just plug into any of the experiments here, plug in your data, and you can solve for the rate constant. It doesn't really matter which one you pick, except I have this one already laid out here. So now I'm going to plug in the 1 here, whoopsie, and plug in the 1 here and actually solve for K. So let me pause and then I'll come back. Okay, so if you plug it in and you solve for K, including your units, you need units for this. So your units for the rate, if you go back to the table, were moles per liter second. That's what these units were here. Right? I'll just do the units. And the units over on this side were what you're really multiplying. K times is moles per liter, and then you're multiplying that times moles per liter, right? So your units on the left side are moles over liters seconds, and your units on the right side come out to be moles squared per liter squared. And then you have to divide by that. So the units for K turn out to be moles per liter seconds divided by, I'll get the divided by line in there, liters, I lost it, divided by liters squared over moles squared. Okay? So when you divide by a fraction, you really invert and multiply, right? So it's like multiplying by moles over liters. So basically, you're taking, when you divide by a fraction, you invert and multiply. So what you really have going on are, I'm going to try, you have moles over liters seconds times oh, I already inverted. You should be dividing by times, liters squared over moles squared. Up here you should have divided by moles squared over liters squared. I had it backwards. So anyway, this cancels out one of the squares and this cancels out with that. So your leftover units are liters over seconds times moles, because you have to invert, you divide by this to get K by itself, and then you invert and multiply. Alright, we'll do more with those units. I think that's it for today. That's about all I have the patience for. Do those sample problems. I think I said 19 through 29 odd in your textbook, chapter 12. I will postpone the test. We'll talk more about it tomorrow. Check over all of your work, please, all of your homework answers, and we will see you tomorrow, hopefully. Bye-bye, guys.